vectors which are orthogonal to the set S. Therefore, this is an important property we have seen in the last lecture, and we have proved it. After this, next theorem we have next point we have seen is a definition of orthonormal set. Definition of orthonormal set in simple language, one can say this is the collection of all mutually orthogonal unit vectors, right? All the vectors are mutually orthogonal to one another, and all the vectors are unit vectors also. We have seen some important remarks on this and a theorem that the orthonormal set in an inner product space is linearly independent. Okay, let us come to today's lecture. We will start with, as I have mentioned earlier, we should start with Bessel's inequality, but as the proof of Bessel's inequality is actually very lengthy, we will just look at the statement only. Okay, therefore in today's lecture Bessel's inequality for, actually these inequalities helps us to prove their theorems. Okay, these are very important inequality. For the first, we will see Bessel's inequality for finite orthonormal sets. Finite orthonormal sets. Okay, orthonormal sets we have seen mutually orthogonal unit vectors. Okay, the theorem statement is, let E1 to En be a finite orthonormal set in a Hilbert space H if X is any vector in H, then prove that. Someone is having their mic to be unmuted. Please unmute yourself. Then prove that. Statement number 1 to prove is summation I from 1 to n modulus square inner product x with x. Number 2, x minus summation I from 1 to n inner product of xei with ei is orthogonal to ej for each j. From point of view, the proof, I don't feel that it is important. Therefore, let's just keep the proof. We will go to the statement directly, right? Then the same Bessel's inequality for infinite sets also there. I'll just write the statement. Bessel's inequality for infinite sets. For infinite sets. Okay. What will be the statement? If orthonormal set in Hilbert space H, then number 1 to prove is summation modulus square inner product xei square is less than or equal to norm square of x. Number 2 to prove is x minus summation inner product xei with ei. This vector is orthogonal to ej for each j. If you just look at the changes, we have changes between the two statements. In the first statement, the orthonormal set we have written is from E1 to En, means it is finite. But that of in the second statement was simply set EI. that I may be anything. No, it's an infinite set. Therefore, look at the statement. Statement goes parallelly. Here only the change is, here we have written summation I is from 1 to n specifically. Here we have not given the limits. Means the limit is depending on your infinite value. Therefore, we are not going any limit. Second statement was almost same for. Okay. Therefore, you have to keep this statement in mind, because this statement may be useful for us for proving the next. Proof is very lengthy. Therefore, we are skipping the proof. Right. Now we'll go to our next definition of complete orthonormal set. Complete orthonormal set. Okay, orthonormal set we have seen. What is orthonormal set? This is the collection of mutually orthogonal unit vectors. Now the meaning of the word complete orthonormal set is actually S is suppose S be any orthonormal set in a Hilbert space, then S is said to be complete if there exists no other orthonormal set containing S. Okay, or in other words, one can say that S must be a maximal orthonormal set. Okay, let me just write it. Let S be an orthonormal set in a Hilbert space H. Okay, S is said to be complete. S is said to be complete orthonormal set if there exists no other orthonormal set, no other orthonormal set, no other orthonormal set containing S. Okay, is everyone getting the point? No other orthonormal set is going to exist which is going to contain S. That is, in other words, here I can write S is maximal orthonormal, bigger one. Right now, S must be a bigger one orthonormal set. Okay. Therefore, one can say that if set EI is an orthonormal set, if it is complete, then it is not possible to adjoin a vector E to the corresponding set. Okay. I'll write thus an orthonormal set. Say EI I am writing. EI is in a Hilbert space is complete if it is not possible to adjoin, not possible EI to set EI in such a way that set EI along with E is orthonormal set properly containing E. Properly containing set EI. Okay, therefore the point to understand is in a complete orthonormal set, the set must be the maximal. Therefore, it is not possible to adjoin the vector E so that EI is orthonormal, because if I adjoin E to this set EI, and if this set EI along with E is orthonormal, then this becomes the maximal orthonormal set, which properly contains E. Okay, therefore the point to understand is in a complete orthonormal set means maximal orthonormal set. Okay, and our next theorem depending on this. Now the numbering I am going to change. This is 16. This is 17. Now we'll go to 18. Okay. Now statement number 18 says that an orthonormal set is complete if any vector, if it is orthogonal to the given set, then that vector must be 0. See, I'll write the statement. An orthonormal set, yes, in a Hilbert space H is complete is complete if and only if for any x in H is such that x orthogonal to S implies x is equal to 0. Okay, to an orthonormal set, if we say that it is complete if any other vector, if orthogonal, then that must be 0. Because if it is not 0, if suppose it is a unit vector, or if it is non-zero vector, then we can convert it to a unit vector. Then it may constitute an other orthonormal set properly containing yes. Therefore, the vector must be 0. Let us prove the result. We will start with part 1. In part 1, we will assume that S is complete. Let S is complete orthonormal set. S is complete. Prove that. We want to prove that for any x in H, x orthogonal to S implies x is equal to 0. This is what we want to prove. Means x is orthogonal to S is assumption. The aim is to prove x is equal to 0. Therefore, we will start with the contradiction that x is non-zero. Assume the contradiction. Assume the contradiction that x is non-zero vector. X is a non-zero vector. What will happen if x is non-zero? As I told you already, if it is a non-zero vector, we can take or we can adjoin the vector with that orthonormal set, and we can convert that non-zero to a unit vector. How can I convert? If x is non-zero vector, how can I find out the vector unit vector? I'll denote it with a symbol E. The unit vector is obtained by dividing with its norm. Correct na? Whenever we do this, what is the norm value? Norm of E is norm of x upon norm of x. Norm x is a scalar taken out. Therefore, we remain with 1 upon norm x into norm x, which is 1. Therefore, this value is equal to x upon norm x is the unit vector. Therefore, this whatever the non-zero vector we have, then let me just adjoin or add this vector to a set E. Thus, yes, union singleton E. Yes, union singleton E is an orthonormal set. Correct na? S is already given to be an orthonormal. X we have assumed to be a non-zero vector. With that non-zero vector, we have formed a unit vector. And yes, union along with that vector E must be an orthonormal set. If it is an orthonormal set, what it should give us? It should give us a contradiction that it properly contains the orthonormal set. Okay, which is a contradiction. What is the contradiction? Contradiction due to properly containing the given set. Okay, therefore let us just write the statement. S union singleton E is an orthonormal set. Here I will write properly containing yes. And if it properly contains S, it will be a contradiction to the set S to be a complete set, contradicting the maximality of yes. Okay, therefore we have started with a contradiction assumption. We got the contradiction, therefore the assumption must be wrong. Hence x must be a 0 vector. Therefore we have proved one part of the result. Let us go for the reverse part. In the reverse part, what we are doing? We will assume let if any vector x is orthogonal to S, then it implies x is equal to 0 and the is complete. Complete means maximal. If I write if S is not complete, what will happen? Yes, can anyone tell me? If S is not complete, what happened? There must be some other orthonormal set in which S is contained, right now? Orthonormal set, some orthonormal set S dash such that, what such that? S is properly contained in S dash. I will write here properly contained, right now? Okay, now in this case, what one can find? As this relation is proper, one can find out an element X which is in S dash but not in S. Right now, properly contained in. This is the situation. This is S, this is S dash. As this is the proper inclusion, we can find out at least one element in S dash. This is in S dash. S dash we have assumed a orthonormal set. And what is the assumption? X is orthogonal to S. Okay. Now see a contradiction. What we are getting? We are saying norm X is equal to 1 and still X is orthogonal to S. But what is my assumption says that to X, X must be 0. Therefore, these two statements cannot hold simultaneously. Therefore, I will write contradicting given condition. Contradicting the given condition. And this contradiction is due to this assumption S is not complete. Therefore, one can say that. So, the assumption orthonormal set S dash exists is wrong. Hence, S is complete. Hence, S is complete. I hope you are understanding the proof. Very simple proofs we are considering here. Right? Any difficulty with the proof?
No, ma'am. Yes, ma'am.
Okay, good. Now we will go to a next point of the syllabus called as conjugate space. We have seen the conjugate space in Banach spaces, no? Can anyone recall conjugate space? Yes? Can anyone recall? N, I think, is the symbol we have used. Here. H star is the symbol. Yes, can anyone recall? Conjugate space in a Banach space we have studied. Both the definitions, both the names are same, symbols are also same. Only the way of defining the spaces is different. Yes. Conjugate space in a Banach space. N star is the symbol we have used, na? What is that N star? N star is set of all functionals. Good. What is functional?
A continuous linear transformation or a bounded linear transformation.
What is functional then? Scalar valued you are forgetting. N to K. Correct, na? That K must be either real or complex, right? Okay. Therefore, a continuous. Now, shall I write here? This is continuous bounded and linear, because whenever we have linearity condition, continuous is implies and implied by boundedness. Therefore, functional is basically a scalar valued continuous linear function, right? And collection of all these functionals we are denoting by n star, which is actually b of n comma k, right? And later we have defined a separate norm on this. What is the norm we have defined? Norm T. So operator norm we have defined na supremum norm T of x. Correct na? X is in the given n on the set of functional, that is conjugate space. We have proved that this is also a Banach space. Conjugate space itself is a Banach space. Now it's a time to define the conjugate space in conjugate space of a Hilbert space. Okay. Here, the most surprising fact for the conjugate space of Hilbert space H is that the conjugate space H star of H with H star is known as Reed's representation theorem for continuous linear functionals on H. Continuous linear functionals on H. The important theorem here playing a role is Reed's representation theorem. We will go to the Reed's representation theorem one by one. Okay, this is a statement of Banach spaces. Now we will come to the Hilbert spaces. In Hilbert spaces, we know that in Banach spaces we have norm as a function defined on the corresponding spaces. But here we have the function defined as an inner product space. So whenever I want to define a scalar valued function, it is not sufficient for me to start with single element, because while finding the inner product, while defining inner product, we need two vectors, inner product of x with y. No. Okay. Therefore, we'll just try to understand how the functional is defined. Okay. And later we will prove it as a functional and we will check how the conjugate space is being defined. Okay. Let us just try to understand. Let this be our Hilbert space H. Okay. And we are defining a functional which must be a scalar valued k. Okay. Now we are defining this as a symbol f, say. Okay. Now suppose I want to define a functional f on a vector x of a Hilbert space H, where the resulting element must be a scalar. Correct? F image of a vector x must be a scalar. But what this f is? Image of x under a functional f should be scalar. But as we are in the inner product spaces, the scalar obtained by taking a inner product with some other element of h. Okay, what is that some other element? Let us fix that vector, say y. Let us pick the vector, say y. Okay, now once I fix the vector y, then what we will do? Image of this functional f on x is inner product of x with fixed y. Inner product of image of f, image of x under the function f, that is f of x, is denoted as x, the right hand side will give us a different values. But as we are fixing this y, this scalar, whatever is resulting, this depends on y. Therefore, instead of writing the function simply to be f, we are writing this as fy, because the image totally depends upon the fixed vector y. Correct? Because we are taking the inner product. Okay. Now, in this way, we are trying to define a function. Later, we will prove that this works as a functional on H. Okay. Is everyone getting me up to this? To the functionals defined in the Banach spaces, we are trying to define functional in the Hilbert spaces. But in the Hilbert spaces, we have inner product with us. For inner product, we require two vector. Therefore, finding the f image of any arbitrary vector x, we need to take an inner product with a fixed vector. Once I fix the vector, say y, depends on y. Therefore, simply instead of calling this as f, we will call it as the function fy. Now we will move towards a theorem proving that this must be a functional. Okay, therefore let me write the theorem as, let y be a fixed vector, y be a fixed vector in Hilbert space H, and inner product of x with y for all x in H. Just wait, I'll check whether meeting is. Ah, okay, then prove that. Then prove that fy is a functional. Fy is functional on H, and also prove that norm of y is equals to norm of fy. Norm of y is equal to norm of fy. Okay, if once you understand this construction, how the functional is defined, why the vector fixed vector fy is needed, okay, then we will go for proving that this fy is a functional defined with this relation, inner product of x with y, right? Let us go for proving the first step. In first step, what we will do? We will prove that fy is a functional. And in the second step, we will prove this norm y is equal to norm of f. To prove that fy is functional, how many points should I prove? Yes. How many points should I prove? This is scalar valued, no doubt, because inner product is a scalar defined on the given Hilbert space. For how many points should I prove? Yes, anyone from the student? That is to prove that. Yes, anyone? Proving functional means what we should prove.
Linear and continuous.
Good. It is linear and continuous or linear and bounded. Linear and bounded. Okay. Therefore, first we will go for proving the linearity. For linearity, what we need? We need a linear combination of two vectors. For that, we want to prove that x1 plus beta x2. What is the value? Alpha fy of alpha x1 plus beta x2. According to this definition, we have to go for proving the linearity. According to this definition, we have to go, na? The definition says that this is the inner product alpha x1 plus beta x2 with what? With y, right? Now let me use linearity in first variable in an inner product, which gives directly alpha times inner product of x1 with y added with beta times inner product of x2 with y. Okay, and as per this definition, fy operated on x, inner product x1 with y is fy operated on x1, and here second one is fy operated on x2, and hence linearity is proved. Thus fy is linear. Thus fy is linear. Now let us go for proving either continuity or boundedness. Now actually here we are going for proving the boundedness. And for any x in H, for any vector x in H, what is the modulus value? Proving boundedness means what? We have to prove this kind of inequality, na? Norm of t of x is less than or equals to k into norm of x. This kind of inequality must be proved. But here, as fy is a functional and the resultant is a scalar valued function, therefore norm acting on the scalar valued field must be modulus. Therefore, we will start with mod of fy of x. Correct, na? Which is modulus inner product x with y. Okay, now I'm going to use the squads inequality. What squads inequality tells us? Modulus inner product xy is less than or equal to norm x into norm of y. I'll write a reason by squads inequality. SCHWAR Z, squads inequality by squads inequality. Okay, let me call this as statement number 1. But look at these two vectors involved, norm x and norm y. Though x is arbitrary, but y we have already fixed out. Once I fix the vector y, what about its norm value? May I say the norm value is fixed? Correct. If once it is fixed, may I find, let me write, may I find any vector m y is scalar value. Norm y is scalar value. Therefore, one can easily find out a positive constant m greater than 0. Here I'll write m greater than 0 such that norm y is less than or equals to m. Therefore, the above equation becomes what the above equation becomes mod of fy operated on x is less than or equals to uh, norm x as it is into m. Therefore, this kind of inequality we have proved. Therefore, what it gives us, fy is bounded. Fy is bounded. Thus, fy is linear and unbounded, and hence fy is a functional on it. Functional on h. Okay. One part of the proof we have completed. Now let us go for the second step. In the second step, we will prove norm y is equal to norm of fy. Norm y is equals to norm of fy. We will make subcase. What are the subcase? Depending on the value of y. Equal to 0, not equal to 0. This y we will consider y is equal to 0. What will happen if y is equals to 0? What about norm y? Norm y is automatically 0. Okay, and what is fy we are defining? Fy operated on x we are defining as inner product x with y. Then what will happen if y is 0? May I write fy of x is equal to 0 for all x in h. Whatever is your value, as one vector is 0, inner product is 0. Therefore, if fy operated on arbitrary vector x is 0, therefore may I say fy itself must be 0, which turns out to be norm of fy is equal to 0. Therefore, this is 1, this is 2, both the norm values are 0, hence or thus norm y is equal to norm of fy. This is what for y equal to 0. Now we will consider subcase 2 for y not equal to 0. Okay. Now if from out mod of fy of x is less than or equals to. Okay. Now from this statement from 1, let me write 1. Mod of fy of x is less than or equal to norm x into norm of y. Okay. Therefore, we will just write as mod of fy of x upon norm of x is less than or equals to norm of y for x not equal to 0. For x not equals to 0. Now what we will do? We'll try to form norm of fy. What is the definition of norm of fy? Yes, operator norm. What will be a definition? Shall I write here? Norm of fy. Anyone? Supremum mod fy of x, norm x is in h, and norm x is equal to 1, less than or equals to 1. Many equivalent definitions we have. Therefore, we have to obtain this value. Okay. Therefore, let me just write finding the supremum on both the sides. What will happen if I take suprema on both the sides? Suprema depends on x. There is no x on the right side. Therefore, there is no effect. Suprema mod fy of x upon norm of x. I'll put x not equals to 0 here itself. Less than or equals to norm of y. Okay, which turns out which gives to be norm of fy is less than or equals to norm of y. Let me call it as number 4. Which definition we have used? Not this one, third equivalent definition. Right now, supremum mod fy x upon norm of x. This third definition. Here I will write according to third definition of operator norm. One part of the inequality we have proved. Now our aim is to go for the reverse, that is proving norm of y is greater or equal by norm of y. Okay. Now further, now we will use the definition. Norm of y is supremum mod fy operated on x provided a norm x is norm of y is a unit vector, because the definition is this definition we are writing for unit vectors. But here in this case, y upon norm of y is a unit vector. Therefore, we will replacing x by y upon norm of y. What we will get? Norm of fy is equal to supremum mod fy operated on y upon norm of y, provided norm of y upon norm of y is equal to 1. Correct now? Okay. Now how this definition we are going to use is, we want to find out the relation between these two. That is, I want to remove suprema on both the sides. Norm fy is a supremum value among this set. Therefore, what is the relation between norm fy and arbitrary element of this set? Yes. What should I write here? Arbitrary relation.
Norm fy is greater than equals to any element.
Yes, greater equal by arbitrary element fy operated on y upon norm of y. Correct? Let me call it as statement number 3. Now we'll just try to understand how this fy is operated. Yes, how this fy is operated, we will check. Fy operated on y upon norm of y. According to definition, this is inner product y upon norm of y with y. Right now? See, the definition is fy operated on x is inner product x with y. Therefore, fy upon this vector y upon norm of y is inner product y upon norm of y with y. Now, this 1 upon norm of y is a scalar. Let us take it out by using first definition of linearity. If 1 upon norm of y I am taking out, we remain with inner product of y with y. But what is inner product y with y in terms of norm?
Norm square.
Yes, this
Of
is
y.
norm square of y. Therefore, one norm y cancel, we remains with norm of y. And therefore, fy operated on y upon norm of y is simply norm of y. Therefore, we'll put the value here, not in 3. I think I misplaced the number. This is 5 actually, right? Okay, therefore, we'll put this value in 5. Put in 5. Therefore, what 5 becomes? Norm of fy is greater equal by norm of y. Let me call it as 6. What is the previous number we have given? 4. Norm fy less equal by norm y is 4. Norm fy greater equal by norm y is 6. Therefore, from 4 and 6, norm fy is equal to norm of y. Okay, hence fy is a functional on Hilbert space H such that norm of y is equal to norm of fy. Yes, any doubt with this? Okay,
No,
therefore,
ma'am.
what we have understood from this relation, I'll write this as just a note. Okay, the mapping T, if I take from H to H star. Okay, arbitrary. What is the nature of element in H? It is Y. What is the nature of element in H star? Fy, na conjugate space. But just now we have proved that norm Y is equal to norm of Fy. Therefore, if I define T of Y is equal to Fy, then may I say this is norm preserving map? T is norm preserving map. Correct, na? H to H star, Y to Fy is a norm preserving map. Okay, any doubt up to this? In the next lecture, we will go for a Reed's representation theorem, which actually tells us how the conjugate space of the Hilbert space is being defined. Yes, any doubt for today's lecture?
No, ma'am.
Good. Okay, we will stop here for this lecture. In the next lecture, we will go for Reed's representation theorem. Okay, thank you for watching the lecture.